So I'm very happy to give a talk today. Oh, 1 second. I need to, okay. Yeah, so hello everyone. I'm very happy to give a talk here today. So today I'm going to talk about cleaning Wi-Fi connectivity data sets for semantic localization. So I start talking about sensor data cleaning and use TPERS, a sensor data management system on your CI campus as an example. So there are a large number of physical sensors as well as raw observations on campus, such as Wi-Fi, camera, and mobile devices and the data they generated. And we can build many applications on top of them, such as presence application, which tries to monitor the locations of users inside a building, or occupancy application to find out the number of people in a given area. However, these raw sensor data can be very dirty in practice, which is difficult to build a high quality application. Before we can use these data, we often first clean them. However, cleaning sensor data is very challenging due to the following aspects. First, volume. Data scale is often very large. Second, velocity challenge. Data comes very fast. The variety challenge means that data forms are different. And the last one is the veracity, which means that data can be dirty or of low quality. And this is my today's focus. The dirtiness data can be incompleteness, uncertainty, duplication, and so on, which will be clear later. And this talk will specifically focus on cleaning Wi-Fi connectivity logs to support semantic localization. When your device connects to a Wi-Fi access point, such connectivity logs will contain the MAC address of your device, the ID of Wi-Fi access point you connect, and the corresponding timestamp. This work has been accepted by VeriDB as a research paper and will appear on VeriDB 2021. So first, what's the semantic localization? Given the uncertain information of locations of users and the floor map or space layout, the semantic localization associates a semantic location tag to this user. For instance, you are in room 2065. Such semantic location tag can be building, floor, region, or room. A close problem in sensor network community is called indoor localization, which determines the physical position of people inside buildings. That is the specific coordinate of users. So if indoor localization can be solved, then semantic localization is trivial. However, although many of the interlocalizations techniques can achieve high accuracy, such as centimeters, they are not suitable to be widely deployed. So they either require new hardware, such as installing specific apps on the phone, or new hardware, such as various sensors or devices to connect signals. They can be expensive and are not always allowed to be deployed due to space restriction. So those affordable indoor localization solutions that can be widely deployed often have high uncertainty, leading to semantic challenges. Thus, we propose a semantic localization solution based on Wi-Fi connectivity data, which exists on the existing infrastructures and thus does not require any new hardware. It's also passive and does not require users to install any software on their clients too. So at the same time, we can localize user to a semantic location with 87% of accuracy. Semantic localization has many important applications in real life, as location information is the most basic information for many location-based services. First, it can be used to compute the occupancy in a space, which can improve the HVAC to save energy for buildings. Second, it can be used for COVID applications to prevent and monitor in workspaces or locating users in large buildings. Third, it can also be used to construct accurate model of building usage for like space planning. To resolve this problem, we built a locator system which performs semantic localization based on Wi-Fi connectivity data. So the left table is a sample of connectivity data. In the first row, a device D1 connects to Wi-Fi access point WAP3 at time 1:04 p.m. So if a device connects to a Wi-Fi AP, we know this device must be in the area covered by this Wi-Fi AP, which can be a coarse location for this device. This problem has two challenges. The first one is the missing value challenge. Because of the Wi-Fi connectivity data are sporadic. For example, the first tuple indicates that this device D1 is in the region covered by Wi-Fi AP3, and the fourth tuple says that it's in the region covered by Wi-Fi AP1. However, what's the location between these two time stamps? They are missing. So the second challenge is called location disambiguation challenge. Connecting to a Wi-Fi access point means that you are in the region covered by this Wi-Fi AP, but such region can be large, which contains many rooms. So which room am I in is the question we need to ask. Now we formalize the above challenges in database. First, considering missing value challenge. The left table is an example of raw Wi-Fi connectivity table. So when a device connects to some Wi-Fi AP at a time instance, the device not only connects to this Wi-Fi AP at the exact time instance, but also a short time interval around it. So we associate it with a validity interval, which is called a delta. In this example, we assume delta equal to 1 minute for all devices. That being said, when your device connects to WAP3 at 1:04 p.m., you are actually in the region covered by this Wi-Fi AP before and after 1 minute around 1:04 p.m. So this delta depends on the type of devices, and there are several techniques that can be used to estimate it, which is out of our scope in this talk. And by this way, we can create a semantic location table, which is a view to represent the locations of all devices at all time instances. Note that the semantic location table is a view and we do not materialize it. So to transform the raw Wi-Fi connectivity table to semantic location table for each tuple, we first keep the device attribute the same and expand the time point to time interval around it. So in this example, time point 1:04 p.m. is expanded as an interval from 1:04 and 1:05, and we modify the Wi-Fi AP to the region it covers. Similarly, we can transform the fourth tuple in the raw data, and we know D1 is in the region covered by Wi-Fi AP3 from 1:17 to 1:19 p.m. Then, what's the location of D1 in the blank time interval? We create a tuple to capture this and set its location as null. So basically, our goal is to clean such missing values in semantic location table. After cleaning all missing values in semantic location table, we want more fine-grained location. That is, what's the room location of a user inside a region, which is called the location disambiguation problem. So to clean a tuple, it takes the coarse-grained location region as input and outputs the fine-grained location room. And this is today's focus on fine-grained localization. So how can we know the room location of a user given the region? There are several things we can use, and we design the fine-grained localization algorithm based on the following information. First is domain semantics, and the second is the Wi-Fi datasets. If we also have the room level ground truth data, such as some device is in some room at some time instance, it will provide much more information to learn a more powerful model. However, it's often difficult to collect such ground truth data in practice, so we do not assume them in our solution. So as for the domain semantics, there are actually several domain semantics we can explore to do room prediction. Information one is room type and the room owner. So for example, given that Mary is in a region and we want to know Mary's room location, if we know her office is also in this region, then she can have a high probability in her office. If this region does not contain her office, but contains a conference room, then the chance Mary is in the conference room can be probably higher than the other people's office. The second information, for example, if we also know the relationship between people, such as a group of people, then we can guess they will have a relatively high probability to be co-located. Information three, if we also have the calendar and we know the schedule of events, so for example, we can guess IS3 members will attend IS3 seminar in a known room and time. So of course, more domain semantics, better results. However, many domain semantics are not always available in practice. So to make our solution as general as possible, we use the minimal domain semantics, that is the room type and the room owner if possible. Based on such information, we compute a probability called the room affinity, which is applied to measure how possible a user is in a room. Second, we have Wi-Fi connectivity data and what information we can get from such data. We show that we can learn the co-location relationship between devices. For example, we consider the following three tuples. We observe that they connect to same region at approximately same time, which means that they are in the same region at this timestamp. Thus, we can learn how often a set of devices are together in a region from connectivity logs. So, given the domain semantics and the connectivity logs, this slide will give a high-level process of how we address location disambiguation problem. Given that you are in a coarse location which contains several rooms, our goal is to find which room you are in. We create a device node and several room nodes. The weight of the age between a device node and a room node is the room affinity we learned before. Now, if we observe your friend are also in a region which has some overlapping rooms with yours at the same time, and we also know the probability that you two are co-located is high, we can infer that the probability that you are in a overlapping rooms such as R3, R4, and R5 will increase. The weight of age between two device nodes are group affinity. And as we observed, more people, which are called neighbors, we can expand this graph using the affinities we learned before. Finally, we use a probabilistic model to predict the room you are in iteratively. So basically, we have two tasks. First is how to compute the affinities. Second, how to design the algorithm to find the room R star. So in this slide, I will describe how to learn room affinity. Assume that now we want to compute the room affinity of device D1 to room RJ at the time 1:04 p.m. Based on the timestamp and the device MAC, we can find the region this device is in the semantic location table. In this example, this is the region covered by Wi-Fi AP3. So the first space metadata we use is the type of rooms. The rooms can be basically divided into two types: public room, which can be shared by multiple users, and also the private room, such as personal office. We assume this metadata is available for all rooms because it's often easy to get in practice. The second metadata is the preferred rooms for users, such as your office, which is the room you spend most of your time. However, please note that we do not assume this metadata is available for all users, because in practice, not all users have preferred room, or it can be difficult to collect such information. So in this example, among rooms covered by Wi-Fi AP3, the public room is 2065. Preferred room for this device can be 2099, and all the others are private room. For these three types of rooms, we assign them 3 ways to each type of rooms. So basically, there are 2 ways to compute such ways. First, if we have ground truth data, we can simply collect the information like daily trajectories for users and count the percentage of the time a user spends on different types of rooms. And we can simply use that percentage to estimate the weight. Second, if we don't have any ground truth data, we do a heuristic weight assignment following the specific rules based on the space metadata we have. First, we assign the weights in a decreasing order for the preferred room, public room, and private rooms. We assign a higher weight for public rooms than private rooms because most of the time you cannot go to other people's personal office without permission. Although this strategy is heuristic, we empirically show that our algorithms are robust to the values of weights if they follow the above rule. In the right table, there are 4 weights combinations, C1 to C4. In each combination, 3 weights are assigned with different values. The accuracy of the algorithm is robust to such weights combinations. And also please to note that the fine-grained localization algorithm does not simply rely on this room affinity, and we view it as a coarse prior, which can be combined with the group affinity to achieve more accurate room prediction, as I will show later. Next, I will describe how to compute the coarse-grained group affinity. It's defined as the probability that devices are co-located in same region. So in this example, assume that we have 3 devices and we want to compute the probability that they are co-located in same region. The idea here is to use the frequency that they are co-located to estimate the probability. So starting from the semantic location table, LD1 contains the data for device D1. If there exists 3 tuples such that these 3 devices connect to same Wi-Fi AP in approximately same time interval, we know that they are co-located in this region. We call such tuples as intersecting tuples. The coarse-grained group affinity is equal to the number of intersecting tuples divided by the number of R tuples for D1, D2, and D3, which is the frequency that they are together. Now we compute a more fine-grained group affinity, which is defined as the probability that a set of devices D are all co-located in room Rj at time t. So first, we construct a device location graph. In this example, we have 3 devices, D1, D2, D3. So given the region device D1 is in, we create room nodes and device nodes, and add edges between a device to its candidate room node. The weight of the edge is the room affinity we computed before. Similarly, we can expand the graph for device D2 and device D3. And then we add a hyper edge for the device nodes, and the weight is the coarse-grained group affinity, representing the probability that they are in the same region. Next, we find the overlapping region for these devices. And in this example, they are room 2069, 2099, and 2091. So if the room Rj, we want to compute it for this group affinity, it's not in the overlapping region, then it's easy to see the fine-grained group affinity will be 0. Otherwise, we can compute the fine-grained group affinity using the room affinity and the coarse-grained group affinity we computed before by applying total probability theorem. So far, we have computed all the affinities. Now we are going to describe our iterative algorithm to find the room using the above affinities. Assuming in this example, we want to know the room location of device D1 at the time 1:04 p.m. That being said, we want to clean the following tuple by replacing W-Wi-Fi AP3 to a room in this region. So device D1 is in the region covered by Wi-Fi AP3, which contains room from R1 to Rk. And we call these rooms as candidate rooms of device D1. At the same time, we observe some devices that share same candidate rooms with D1, which are called neighbor devices. The location of these devices can possibly affect the room location of D1. Thus, we predict the room location of D1 based on these neighbor devices. Specifically, in each iteration, we pick a neighbor device for unprocessed device set to processed device set, and compute a conditional probability for each room based on the processed neighbor device set. This conditional probability is the probability that device D1 is in this room when we observed the processed neighbor devices. Next, we check the stop condition. If the algorithm gains enough confidence for the current answer, then the algorithm stops and output the room with the highest probability. Otherwise, we continue the algorithm until the stop condition is satisfied.
Yiming.
Oh, sorry.
Yeah.
Yeah. Okay.
Great. I think somebody else is trying to ask a question as well.
Oh, so any questions so far?
Okay, so I guess let me ask you a question. So how do you pick the neighbor devices, and what is it randomly picked, or is it picked in an order, and is it order dependent or it's independent?
Okay, so for now it's randomly, but the optimization strategy I will describe later. We'll focus on this part. Yeah.
But is the eventual answer, the probability you get, is that order like, imagine, is it possible that if I go in a particular order, I may get a different answer, and if I go in a different order, I go get a different answer? Can that happen?
So basically, I think I will focus on these parts in the next slides because it's one of the optimization strategy. It will focus on the order of the neighbor devices we pick. Yeah, and I will show the effects.
So, Yiming, there is one kind of assumption that's being made when you get to this step is that D1 is only connected to one Wi-Fi access point, right?
Yeah, yes. So I think it's because the data we use is the Wi-Fi connectivity log, right? So at one time instance, a device can only connect to one specific Wi-Fi IP. Yeah.
So this, if we were to use something like this, this kind of methodology will not work when you have things like RSSI.
No, so I don't use such information.
I know you don't, but if the general methodology, will not work if you use RSSI, right? Because you are probably.
Yeah, so so basically, a device can have the RSS information for all the around the Wi-Fi APs. So not only for the Wi-Fi AP it connects to. Yeah.
Right, and the one it connects to may not necessarily be the one with the highest RSSI.
Yeah. Yes, I think so. Yeah.
Okay.
Yeah. So here we have two tasks. First is how to compute this conditional probability. Second, what's the stop condition and how to determine and how to terminate the algorithm early without computing all the neighbor devices. So to compute the above conditional probability, first we assume neighbor devices are conditionally dependent, and in this case we can compute the probability using room affinity and the group affinity we computed before by applying total probability and the Bayes theorem.
But can you give us intuition? What does it mean to have the neighboring devices are conditionally independent? What do you mean by that? Semantically, what does it mean?
So basically, that means so the location of a neighbor device will not affect the location of the other neighbor device, right?
Okay.
Yeah. And in the second case, we relax the independent assumption before.
So if I get it correctly, what you're saying is, imagine that there are 3 people in the same region,
Yeah.
along with me.
Mhm.
The location of, let's say, person 1 will affect me, location of person 2 will affect me, location of person 3 will affect me, but they'll affect me independently.
Yeah, yes.
All right.
Yeah. So now we relax the independent assumption before, and each neighbor device may not be independent again. And in this case, the relationships or ages among neighbor devices are measured as the group affinities we computed before, which is the probability that a set of devices are co-located in a room at some timestamp. This way, we can treat the neighbor devices as set of clusters, where every device inside a cluster share high group affinities above a threshold with the rest of the devices, and every device in a cluster share low group affinities below a threshold with the other cluster. Thus, we can treat each cluster independently. And we can now compute the room.
Oh, hold on one sec. So when we define these thresholds, this threshold can be used to define groups of people who are always co-located or who are frequently co-located based on that threshold. Or it could also be used to define a group of devices that are always together, such as your laptop and your phone, depending on how you set the threshold. I don't know whether you actually indicated that earlier, right?
Mm.
But it could also be used to capture device. When you say device affinity, it could be a group of devices that move together or a group of people that move together.
Yeah, so actually here, we do not disambiguate whether or not the two devices belonging to same user or not. So yeah,
Right.
it can, yeah.
But the thresholds might be set differently. Like, you may frequently meet with somebody who you're working on a paper on or who works in the same topic as you or because you're in the same office. But, that the threshold you would set for that might be different from the threshold that you would set for your watch and your phone.
So I think the threshold here is set for the group affinity we computed before. Yeah. So
it's an experimental parameter, right? I mean, it's empirical.
Yes. Yeah. Yeah. So in this case, we can compute the room conditional probability using the room affinity and the group affinity we computed before, by applying the total probability and the Bayes probability theorem. Next, we consider what's the stop condition of this iterative algorithm, and can we stop it early without processing all the neighbor devices, which can be huge, which can be a large number in practice. So to give a high-level idea, we can stop the algorithm based on the following 2 facts. First, if the probability for some current room is very high in current iteration. Second, if we can make sure that those unprocessed devices are unlikely to change the currently answer. So to capture those unprocessed devices, we define 3 probabilities, which are expected P, max P, and min P. So the expected PR is the expected probability that R is the answer based on both processed and unprocessed devices. And similarly, max P and min P are the maximum and minimum probability. We showed and proved that these 3 probabilities can be computed as follows. First, For the expected probabilities, we show that it only depends on the processed neighbor devices. That being said, is equal to the conditional probability of R being the answer based on the current processed neighbor devices. And the max probability can be achieved when all unprocessed neighbors are also in room R. The mean probability can be achieved when all unprocessed neighbors are not in room R. And we also show that if all unprocessed neighbors are in room R dash with the highest probability other than R, then we can achieve the mean probability. So based on these three probabilities, we can set the stop condition. So if there exists a room Ri, for any other room Rj, if we have the mean probability of Ri is greater than the max probability of room Rj, then we can stop the algorithm. But actually, this condition is often too strict. So we lose the stop condition as follows. First, if there exists a room Ri whose mean probability is greater than the expected probability for all the other rooms Rj, then we can stop the algorithm. Or if there exists a room Ri whose expected probability is greater than the max probability for all the other rooms, then we can also stop the algorithm. So the second optimization strategy is to make the iterative algorithm converge faster. In the algorithm we talked about before, we select the neighbor device randomly. However, we empirically shows that if we pick the neighbor device in a decreasing order of their group affinity to the query device, it will make the iteration converge much faster. So the behind intuition is that the neighbor with a higher group affinity to the query device often has higher impact to its room localization. If we deal with these devices early, it would be helpful to terminate the algorithm faster. So the question is how we can estimate the group affinity efficiently. Our method is using caching. In particular, we cached all the pairwise group affinity in the past queries. In this example, we have three past queries, Q1, Q2, Q3, and we use only pairwise group affinity to build three local affinity graphs. So in figure A, the nodes are devices and the edge weights are their group affinity. To know that in this strategy, we only cache the pairwise group affinity for a low capacity, and they are shown to be enough for estimation. Next, we maintain a global affinity graph by merging the local affinity graphs, where the nodes in the global affinity graphs are the union set of the nodes in local graphs, and the edge store all the past affinities between two nodes. For instance, we look at the edge E12 in global affinity graph. It stores three affinities between device D1, D2 from past queries in three different timestamps. Now, when a new query comes, say query Q4, and we use the global affinity graph to estimate the affinity between the queried device, which is D2, and its neighbor devices. In this example, the new query Q2 is asking the location of device D2 at the time 1:30 p.m. Now we need to estimate the affinity between D1 and D2 using the cached affinities, which is assuming to be 9 a.m., 1 p.m., and 4 p.m. in this example. We compute affinity by assigning a higher value to those time instances that are closer to the query time. Among the three past affinities between D1 and D2, the affinities at 1 p.m. is closest to the query time instance, thus it can best represent the affinity between them, and thus we can assign a highest weight. To capture this, we simply use a normal distribution where the mean is time t and standard deviation is 1. So far, any questions? Okay. So for the evaluation part, we use the real data set captured by Wi-Fi sensors in DBH building for 6 months, which contains around 38 million of connectivity events for 94,000 devices. We connect ground truth data from volunteers by logging their daily trajectories and also from camera. As for the baseline of fine-grained algorithm, so given a region, baseline 1 randomly pick a room as the room location, while baseline 2 always select its office room as the room location for the query device. As for the quality metric, we use accuracy as a quality metric. So given a query on the ground truth data, the answer of this query can either be outside the building or the room location the device is in. Thus, the third accuracy, overall accuracy, is defined as the proportion of queries to return correct room and outside. Recall that the output of the coarse-grained algorithm is outside or the region the device is in. So if the region it predicts contains the true room location, we say that this is a correct prediction for the region. Thus, coarse-grained accuracy is the proportion of the queries which returns correct outside or the region. Given the region is corrected predicted, the proportion of queries that returns correct room is defined as fine-grained accuracy. So to show the accuracy of the algorithm, we first classify the users in different predictable group based on the time they spent on their office. So for example, the group 40 to 55 means the user in this group spent 40 to 55% of their time in their office. So higher percent of such time, more predictable the group is. Oh, sorry. And we report the accuracy for different group of users as well as the overall query set queue. So each cell in the table contains 3 accuracy, which are accuracy for coarse-grained, fine-grained, and the overall method. We focus on the fine-grained accuracy, which is covered as green. Locator outperforms all baselines in those less predictable groups, except in the group 85 to 100. And in the overall query set, the I locator is the locator under the assumption that neighbor devices are independent. And the D locator is the locator under the assumption that devices are not independent. And we observe that they can achieve the accuracy for 83 and 89% on average. So we
in the previous graph, why is it the case that locator does not outperform baseline 2 in the 85 to 100 group?
So because baseline 2 will always select the office room as the room prediction, right? So in this case, the group, the user in this group will always spend like 85 to 100% time in their office. So the baseline 2 in this group, the accuracy is very high. That's why.
I see.
Yeah. So here we explore the size of historical data we use. So basically, we use historical connectivity data to learn the affinities in the fine-grained algorithm. We explore how the amount of historical data before query time affects the performance of locator. So the axis is the number of the weeks of the data we use, and then the Y is the accuracy. The following 3 pictures shows the accuracy for coarse, fine, and overall algorithm. We focus on the fine and overall accuracy here, and we observe that fine-grained algorithm and locator will require like 3 and 5 weeks of historical data to learn affinities. For fine-grained algorithm, after 3 weeks, more data would not increase the accuracy of the algorithm. Here, we show the result on simulated data set. So we use a simulator called Smart.
Can we go back to that previous graph?
Yeah.
I'm just trying to
Yeah.
look at what are all the lines here. I mean, I get the general trend, but so can you explain that, the difference between these different lines?
So basically, the I find here is the fine-grained algorithm based on the assumption that all the neighbor devices are independent.
Oh, yeah.
And this is only for the group for the 40 to 55%, because this group of users are most difficult to predict, right? Yeah. So we explore for two groups, which are 40 to 55% and 55% to 70%, because these two groups are most difficult to predict. Yeah.
So I mean, let's get a real idea here, because you're doing the experiment on the place where we used to be there, right?
Mm-hmm.
At what accuracy level can you predict where I am? Let's come to the bottom line, right? So, where am I? Like in this realm of predictability, am I a person who's, let's say, 40, 55%, or what am I?
So I'm not sure the distribution of time spending for your data. So let's assume that if you are in the group like 55 to 70%, right? If now we get 3 weeks of your historical data before query time, so actually we can achieve like 85% of accuracy in this case.
So effectively, you'll know 85% of the times where I am.
Yes. Yeah, because that's the define of the accuracy in this case, right?
Interesting.
Yeah.
And is there an explanation for why the overall locator results turn out to be a little bit more smoother, and there's a little kink in the graph in the fine-grained?
I think it's a combination of the both fine-grained and coarse-grained. If you observe the trend in the coarse-grained localization, right? So actually, it takes more historical data to converge. So the locator is a combination of the both part. So I think that's the reason why it can require more historical data to learn the affinities.
Have you tried this over specific people to see how well it worked out? Like maybe Chen, and see, hey, follow Chen around for a day or two and see.
So actually, this is contained in the volunteers data in our ground truth data set, right? So actually, we asked the volunteers from our group and also some users in analytical group to log in their daily trajectories. Yeah. Yeah.
How well did you do in that?
You mean how to collect the daily?
No, how well did you do? What was the accuracy levels of these guys?
Yeah, I think this is reflected in this graph. Yeah, because this is based on the ground truth data we collect, right? Yeah. And for now, we don't have the more ground truth data for the other people because it's kind of private. And yeah.
No, but I thought you were using camera to sort of localize, right?
Yeah.
So you had you have a way of creating a larger ground truth if you want to.
Yes. Yeah.
Somebody has to sit and watch it though.
Yeah, we can.
All right.
Okay. And here we show the results on the simulated dataset. We use a simulator called Smart Sim to simulate the following 4 scenarios: office, university, mall, and airport. And look at the table below. each cell in this table contains 3 values: the accuracy for the coarse grained and the fine grained and the overall of the locator. And the value in the bracket is the difference between overall accuracy of locator and the best baselines. We observe that the locator outperforms the best baselines for all profiles up to 30%, and it also performs better for more predictable profiles. So
in this result, the graduate student and staff are more predictable.
Yeah, yes. You mean in the university scenario?
In the university setting,
yeah.
Right?
Yes. Yeah, so the last experiments, we tested the scalability of locator. So basically, we select the subspaces of DBH building and use these 3 parameters to control the size of the subspace. And we also do it for the simulated data sets, which is the mall. And we plot the average running time per query on both real and synthetic data set for combination of techniques. So the plus C here means that we use the caching technique. So basically, we can observe that the caching strategy will decrease the computation time of the locator very significantly. And with the caching technique, locator has a great scalability when the size of the space increases to large scale. And it can also support a near real-time query response. So the conclusion is locator.
So how much is the time again? Let's have a look. Even with the caching, how much is the time?
Yeah, so so for the iLocator, it's around like 300
milliseconds, right?
Yeah, and for the locator with caching is around I think it's around it's around 31 second.
Or 1 second.
Yeah.
Okay, but imagine if I'm asking a query for this is per event, right? This is per move per location of a person, right?
Yeah.
If I want to ask a query, let's say how many people are there on the 3rd floor right now, or whatever it might be, or in 2065 right now, correct?
Mm-hmm.
You're running these queries over and over again for each person.
Yeah, so
another 300 milliseconds.
Yeah, so in that case, it's not efficient because because locator is designed to support an online query. So if we want to do some batch cleaning, then we need to design some more efficient algorithms to do some group cleaning instead of to clean each tuple one by one. Yeah.
Okay.
Yeah, so basically the conclusion is locator is passive. It doesn't require any new software and it's also off the shelf. No modification to existing infrastructures and no new hardware. It's also general, no special setting to the hardwares. And the performance is that, so basically for the coarse, fine, and overall, it can achieve like 82, 83, and around 80 accuracy. And half second, 1 second query time on average for iLocator and dLocator. Yeah. So thanks, this is done. Any questions?
So Yiming, I have a question.
Yeah.
So so the kind of uncertainties or errors that you kind of dealt with were missing data and the fact that, if I'm getting Wi-Fi connectivity data, it has a broader range than one room, so I don't know exactly which room the person is in, right?
Yeah.
Those are the 2 types. Now, if I I guess this may not be an issue for Wi-Fi access point data, where timestamps are fairly accurate, and there may be some kind of clock synchronization NTP or something running across all of the different access points. So the timestamps you're assuming that it's accurate and synchronized, right?
Yeah. So for the timestamp, we assume that they are accurate. Yeah.
So I'm just curious if it might be worthwhile running an experiment which kind of says, if I intentionally messed up the timestamps,
Okay.
what would be the accuracy that I would get? At which point does it start impacting the accuracy of the technique? Or am I even tolerant to errors in timing?
Yeah, I think this problem can be part of the sub-problem in the missing value cleaning, right? So if you see the if you view the incorrect timestamp as part of the missing value in the original correct timestamp, then I think the coarse localization can help this problem to some degree.
Yeah, it may not even be missing, right? It could be, you entered the building, so you went to access point 1 and then you connected to access point 2. If the timings were messed up, it would look like you went to access point 2 and then to access point 1, which could be interpreted as you exited the building.
Okay.
So semantically, they could, from a trajectory point of view, they could mean two different things.
Oh, yeah. Yes.
Right? And so errors of that kind can cause, it would be interesting to see how tolerant the technique is, or what additional stuff needs to be done to address, those kinds of time synchronization errors.
Yeah. Yes. Yeah.
Yiming,
Yeah.
I have one question.
Okay.
So, suppose that you saw my office, Roberto office, and Sarada office.
Mhm.
So Roberto and me share the office, and in a day several times we visit Sarada office also.
Yeah.
So in this scenario, even if you collect ground data, your algorithm cannot detect where am I or where is Roberto now, because even we can be in our office or in the Sarad office, and both rooms are connected to the same access point. So how will you
Um,
get the answer?
You mean to differential the room for shared office and your office?
Yeah. So how we can distinguish that? Okay, the exact location of my. I can know by by your system of Wi-Fi access point. Okay, I am under this Wi-Fi access point, but exact location. How can I detect this information?
So I think I can collect some of your data and share data for a real testing.
No, even if you have real data. So because sir never calls me on the fixed time every day. He just pass by my office and call me. Okay, come to my office.
Yeah.
So this is not identical behavior that we follow. Okay, every day we will meet at 11 a.m. or 12 p.m. So anytime we met in the office. So will the system will detect the exact location, or every time it will say some?
I think the things can be so from such Wi-Fi connectivity logs from your data and shared data. At least we can learn that you two will share a relatively high group affinity. And for the if there comes a query to ask like the location of you now, and now I think the algorithm will start because because Shard has high probability in his office, right? And you will have a relatively high probability in your office. But at some timestamp, the group affinity between you two guys are very high. So which room you are in this case, right? So I think the algorithm now will try to find actually, in this case, I'm also not so sure.
Actually, sorry to interrupt you, Jimin, but like Santanu, take into account that in that specific situation, so you're connected to a Wi-Fi access point that covers 10 rooms. In among them is your office and our office, and then Sarat's office, right? So what Jimin is saying is that he can create, like, based on the of this data, knowing that you connect frequently at the same time that Sarat and so on, right? He can know that probably you have some affinity towards your office and towards Sarat's office, because that's the office towards which Sarat has a high affinity. So at a given point of time, if you ask the algorithm, where am I? Sometimes the algorithm is going to say in your office because you have a higher probability there. Sometimes it's going to say in Sarat's office, and then there could be a problem there, right? Because sometimes you can be in Sarat's office and the algorithm might say in your office, right? But the algorithm is going to filter out of the 10 rooms. It's going to say that most likely with a very high probability, you're not going to be in Nalini's office, for instance, right? So yeah, sometimes it's going to make it like point errors. Sometimes it's because it's all based on probabilities, right? So sometimes it will say you're in your office when in reality you might be in Sarat's office. But at least from that list of possibilities, it's going to filter out almost completely some of them. But yeah, these problems might occur in those situations. The algorithm might say that you're in your office when in reality you're in Sarat's office, because that's very difficult to do.
Yeah, I think it can sometimes go wrong in the case you mentioned. Yeah.
And recently we were writing with Sarath something like about Wi-Fi access point and signal strength and angle of arrival and time of arrival and one more parameter that he wrote. So if we will include this thing in your algorithm, will the accuracy will improve at that time?
You mean what parameter?
And the signal strength, time of arrivals, and angle of arrival, some these types of parameter. So if we will include in your you are collecting Wi-Fi connectivity data, and if I will give you additional data, so I think that accuracy will improve.
Yeah, it might be, but in this way, you can view the introduction of such parameters as a way to decrease the initial range of the location, right? So because the initial cost location for a user is the region covered by the Wi-Fi AP it connects, and after you introduce such parameters, it can decrease such cost range to some degree. Yeah, but the location disambiguation challenge still exists. Yeah.
Yiming, let me ask you a very different question.
Okay.
So it's interesting, and you applied this to the setting of, let's say, location and sensor-based data in this specific example or case, right? But let me replace room by, let's say, paper, okay? And let me remove, well, I guess the person in the room, that person remains a person except becomes the author, for example.
Okay.
Right? So I have an author disambiguation problem, and there are a lot of reference disambiguation problems of this kind, where I don't know if this Mike Carey is MJ Carey or MK Carey. We don't know yet, right? For example, there are ambiguity, or Chen Li is a better example. So there are so many Chen Li's around, right? So for example, we don't know which one it is, correct? Would this technique apply in that setting?
I think yes, because it's basically like connecting based on the relationship between different entities. So I think yes.
You should then compare your work to, there's a lot of body of work on relational cleaning and on cleaning basically disambiguating entities, right?
Yeah,
So
so
you can
yeah,
apply and you can sort of actually experiment and see how well this technique works.
yeah. So actually, we compared those work in the related works of the paper. Yeah.
No, but do it experimentally is what I'm saying.
Okay.
So on their apply your technique on their problem.
Okay, I didn't try yet. Yeah.
Yeah.
I will. Yes.
All right, I guess we are actually out of time. We are above time a little bit.
Any other question? Okay, so we can.
Let's thank Yiming.
Yeah.
Let's talk.
Oh, yeah.
Thanks, Yiming. So whenever I will get the video, I will upload it.
Okay.
Okay. Bye.
Bye.
Bye.